class now. Okay, I've already told you that we will start the class. Okay, so good morning everyone, morning once again. So today we are starting a new chapter, which is elasticity, right? Okay. Okay, so yeah, actually that I thought that that will be a mixed chapter, Abhiram. That's why. So first we will be studying fluids because they are two different chapters. Okay, so I have this conception that both are mixed, right? Because when I studied both chapter together. That's why. Okay, but for you it is different. Okay, first we'll talk about solids, then we'll talk about fluids, right? Now, when we talk about this chapter, think about this chapter. Okay, so before starting this chapter, I would like to ask a simple problem, right? When we talk about solid or when we talk about any material, okay, so what do you think? What can we think about the nature of material? Think about it, right? For example, when you talk about rubber or pen or your textbook, right? So we talk about these materials which is around us. So what can we talk about the nature of those materials? First, they are solid, right? I'm talking about the solid materials only. Okay. What about that? After that, right? What can you say about the nature of those materials? Tell me. Think about it. Are they strong? Are they weak? Right? They are, yes, right? So they have intermolecular distance, okay? And just think about it, right? Whatever we know about solid materials, right? They are rough or smooth, okay? They are rigid, okay? Let's think about it. I'll just pen it down, okay? I'll just pen down all the properties that you guys are saying. Okay, so first, intermolecular force, right? Intermolecular force, molecular force, which is basically strong, right? I'm talking about solid. Then some people are saying rigid, okay? And think about it. Brittle, okay? Brittle, okay. And ductile, very good. Ductile, okay. Smooth, rough, okay. Malleable, okay. Okay. Now melting point and all those things will come into intermolecular forces only, right? So we won't be going into chemistry or thermodynamics part. We just talk about the physical nature, okay? Right? So mostly about these things. So we'll be talking about these things. There's one more property. Tell me. I'm waiting for. What was the name of the topic? Tell me, what is the name of topic? Yes, elasticity. So I can say that elasticity, right? Okay, or plasticity. Now, we will start with the basic introduction of this chapter. What is the meaning of elastic substance? Think about it. What is the meaning of elastic substance? If I have to ask, because we all know, right? We all know the term elastic since our childhood, right? But when I ask you, what is the actual meaning of elastic substance? Tell me from your observation. Just tell me what is the meaning of elastic, right? Substance. Yes, very good. So I can say that if I have to tell that what is the basic meaning of elastic substance, I can say that okay, any substance which regain their shape. For example, when you talk about rubber, right? Rubber. So rubber will regain their shape, right? When you stretch it, when you stretch a rubber, then after some time it will regain their shape. So I can say, that, okay, rubbers are elastic, right? Yes, very good. Spring, very good, right? So springs are also elastic. Anything else? What about Sponge, okay, very good. Sponge, very good, right? So rubber band is rubber only, right? So these are elastic. What about your chalk? What about your pen? Okay, what about steel? Steel. Elastic or non-elastic? Okay, steel, not steam. Samarth, it's steel, right? Iron, steel. Now, the thing is, right, for now we have this perception, okay, that a substance which can regain its shape like completely are elastic substance, but that's not true, okay. So I can say that the extent of elastic nature may vary from one substance to other substance, okay. It might happen that some substance which we think as non-elastic may have some elastic property up to some extent, okay, right. So we will be discussing what is the reason of this elastic behavior, right, what are the factors and how to calculate it, right. Now, for this, steel is elastic, steel is highly elastic, okay, steel is highly elastic, right. We'll just discuss how, okay. Now let's see what is the meaning of these things. Now, first of all, when we talk about substance, we talk about its strength, right, strength of substance, how strong any substance is, right everyone, right. So when we talk about strength of a substance, strength of a material, what are the factors that we consider? Think about it. What are the factors that we consider? Right? For example, uh, you say that this material is strong, this material is weak, right? What are the factors that we consider for that? Okay, yes, hardness, okay. Anything else? Okay, hardness, softness, rigidity, okay. So have you heard of word called stress and strain? Ductility, okay. Yes, so I can say that, yes, very good, Srihari. So you can also say that, okay, how much force it can experience before breaking, right? Okay, or how much force it can sustain before deforming or before fracture, right everyone, right? Okay, now what's the meaning of these terms? What is the meaning of stress, right? Because when we talk about strength, we talk about a term called stress. Now before talking about stress, right, just think about more basic thing, right? What happens? Well, what happens when we try to deform anything? Think about it. What happens when we try to deform anything? Suppose when you try to stretch a rubber, okay, or when you try to push a sponge, right? What happens? What basically happens? Think about it. We apply force. Okay, very good, right? So when we talk about, let's talk about a rubber. Okay, let's talk about a rubber which is like of this length, suppose. Okay, just like this. Yeah. Okay. Now suppose you apply a force, right? It is a rubber. It is a rubber. You apply a force in this direction. It is your applied force, right? Or it is your driving force. Now tell me what will happen here. Tell me what will happen here. Think about it. Think about what will happen. Just from your observation, what will happen if you try to pull a rubber, right? If you try to apply a force, what will happen? Like obviously you're pulling from the both side, okay, right? Yes, so rubber will try to expand, right? It will try to stretch. So from this, it will try to stretch like this. Agree? Got it? Yes. Now, if you apply more force, then what will happen? Think about it. Then what will happen? It will stretch more, right? It will stretch more first, right? Breaking is again the extreme point, right? You try to stretch more, yes or no, right? It will stretch more. I can say that if you apply more force, it will stretch more, as simple as that, right? Got it? Right? So there's one thing which I can deduce from the normal real life experiment that we all do. We all love playing with rubbers, right? That if we apply more force, that will stretch more. Okay, so I can say that, okay, there's one thing which I know, right? If I apply more force, it will stretch more, like length will increase. Okay, but is this correct deduction? Is this all the factors that we need to consider, or is there any other factor? Think about it. Yes. Now think about it. Suppose we take instead of this thin rubber, suppose we take one thick rubber, right? Suppose we take thick rubber, whose this area is like 3 times of this. Now tell me, suppose if we apply same force that we applied in this case, will it stretch up to same distance? Tell me, will it stretch up to same length? Yes, more or less. It will expand, it will stretch more or less, right? That's basic common sense, right? It will stretch less. Very good. So I can say that there's one more factor which is contributing to the, right, expansion of this rubber, right? Or not expansion, basically the stretching of this rubber. It will be less now, because see, the thickness is more, right? Just try to think about it. Take one rubber and take 3 rubbers and try to stretch. Okay, in order to stretch, you have to apply more force. Have you observed this or not? Anyone have observed this? Tell me, guys, anyone? Have you observed this? Right? Okay, yes. So I can say that there's one more factor which is responsible for this, and that is the area. So I can say that if I want to find a parameter which can measure the strength, right, or which can measure the elasticity of any substance, right? So it is something related with pressure, which is F by A, force per unit area. Now, but think about it. Which force I'm talking about? If I want to talk about the elasticity, which force I should talk about? Should I talk about this force? Should I talk about this driving force, right, which I'm applying to stretch something? Tell me. Should I talk about this force? Tell me, guys. Because if it want to regain its shape, right, if it want to regain its shape, right, this object should also have a restoring force which is in opposite direction of this, right? So this is like F restoring, yes or no? Yes or no? Think about it. Right? Okay, got it. So I can say that here, I can say that, right? Depend, yes. So it does not depend, it does not depend on this force, right? Okay, how much a substance will regain its shape. It depends on restoring force. Yes or no, right? Okay, so just think about it. Just think about it. Suppose I'm having a spring. Let's try to understand this, right? I hope all of you understood uh, the idea that if we stretch more, right? If we apply more force, it will stretch more, right? I hope all of you understood this concept. Now let's take example of spring. I hope all of us have played with this spring. Now think about what happens when you try to stretch the spring. What happens? What you observe, right? I don't have spring here, but I would have shown you. Suppose you try to stretch your spring, okay? You applied a force in this direction, right, everyone? Now, what do you feel? Just think about it. What do you feel? Yeah, any spring, right? What do you feel? Think about it. Tell me, guys, what do you feel? Inward force, yeah, right? Right? There's something which is again pulling back the spring in this direction. Yes or no? Right? Yes or no? So this is your restoring force. This is your restoring force, right? Now, if we talked about the intermolecular level, what happens? Think about it. We know that two atoms. When you talk about two atoms, right, they are normally stable under some fixed distance, right, which is your internuclear distance. Yes or no? Tell me yes or no, right? If you talk about on interatomic level, okay. Now we know that this is the stable distance for any two atom. If we try to pull it away, it will try to pull it away. It will try to again come closer for the stability because of the force of attraction. Yes or no? Intermolecular force of attraction. Yes, everyone, right? Okay. So I can say that that might be one of the reasons for this restoring force. Yes or no? Right? Yes or no? Got it? I hope all have understood this. So if we talk about this force per unit area, right? So if this force is the force applied by us, which is your driving force, then this term will become pressure. Agree? Agree, right, everyone? If this force is driving force, if this is the force that we are applying on any object, right, then it is your pressure, because that's the basic definition of pressure, right? Now what about this term? When we talk about restoring force per unit area, then what is this called? This term is called as stress. Okay, this term is called as stress. Got it, everyone? I hope all of you understood this, right? Anyone have any idea? Got it? I hope all of you understood what is your stress, right? So yes, technically it is a kind of pressure, but it is not the force which we apply. It is the force which is applied by the object, which is a restoring force. Now think about it. Can restoring force ever be more than this F? Can restoring force ever be more than driving force? Think about it, right? No, very good. It can never be more than, right, driving force. It will always be less than driving force. Got it? Right? Okay. So I hope all of you understood what is strain. I hope all of you understood what is strain. Sorry, what is stress? Yes, Samarth, right? Stress is kind of tension only, right? Okay. It's just the name that we give. Okay. Got it? Because when talk about tension, tension is just a force. Okay. Tension is just a force, right? So if I talk about a wire, okay. So this force, restoring force is your tension. Got it? Right? But this force per unit area will become your stress. Got it, Samarth? Right? Got it? Okay, now I hope all of you understood what is stress. Now let's think about it. Let's think about it. The same example that I was talking about. Okay, now let's take one again, a wire. Okay, now I know that if I want to apply a force, right? Let's apply a force in this direction, which is your F. So this wire will have a force, right, in opposite direction, which is your F restoring, which will try to make this wire, right, to gain its shape if you try to stretch it, right, everyone? Tell me, right? Now suppose the length of this wire is L. Length of this wire is L, okay? And this changes delta L. Delta L, right? This is change, which is delta L. Got it? Now think about it. Think about it. If, and can I say that if force is more, restoring force will be more, yes or no? Think about it. If we apply more force, then the restoring force should also be more, yes or no? Because this restoring force is like friction, right? Don't you think that the restoring force is like just like friction? The more we apply, the more restoring force will be there. Yes. So can I say that? Okay. I can say that if I am applying more force, this length will be more, right? This length will be more. Yes or no? Right? But think about it. Can I say that if change in length is more, stress would be more? Think about it. Can I say that if delta is L is more, right? If delta L is more, stress will be more. Can I say that? Think about it. Yes or no? there's a very small conceptual doubt over here, right, that you have to think about. I'm saying that, can I say if delta L is more, if delta L is more, right, then stress is more. Try to understand my problem. Okay, can I say this? Yes or no? So most of you are saying yes, okay. Now let's take another example. Suppose I'm taking one wire in this case, and here delta L is suppose 0.5 centimeter, suppose, right? Suppose I'm just taking one example, and the length is suppose 10 centimeter. Okay, got it? Now, second case I'm taking, okay, the length of wire, right? Again, length of wire is suppose 20 centimeter, 20 centimeter, okay? And this change delta L is like 0.7 centimeter, right? Now tell me, so this delta is more, this delta L is more than this delta L, yes, right? Can I say that stress is more in this? Tell me, can I say that stress is more in this? No, right? Please mute yourself, everyone. Right? No, it is clearly visible that, okay, because the length is more, right? Even though it is changing, the stress cannot be the same. So what I want to know, I want to know the change per unit length, yes or no, right? I should be considering change, right, per unit length. Agree? Right? Agree? Right? So there should be a term something like this, right? So this term is called a strain. This term is called a strain. Okay, right? This term is called a strain. So length, right? When we talk about length, it is the change per unit length, like a uh, unit length of substance, right? A unit length of any solid, right, will change up to what length, right? So that is your strain. So can I say that, okay, now I can say that, okay, this is strain, right? Now I can say, okay, stress should be proportional to strain. Got it, everyone? Yes. Now I can say that, okay, now I can say, okay, yes. So if this is strain, so instead of just saying change in length, I can say that change in length per unit length should be directly proportional to stress, right? Agree? Agree? Everyone agree with this relationship? Yes or no? Tell me. Anyone have any doubt till this step? I'm trying to make it quite easy, quite simple. No? Everyone is getting the concepts, right? Okay. So these are just introduction of the terms stress and strain. Okay. Now, let's think about the type of deformation we can have, right? Let's think about the type of deformation we can have. Now, we have okay, it's quite deformed, I guess. So let's take one. Okay. So let's take this, right? And let's take one more length like this. Okay. And let's take one substance like this. Okay, right? We have three substances. Now we will try to talk about what can be the change in length, right? Or what can be the type of deformation we can have. Now let's think about it. Suppose we have this length, right? Now suppose we either pull it or we push it. Okay, right? Depending on what we are doing, either pulling or pushing, it will contract, like it will either stretch, right? Right? Wait, I'll just use this here. Okay, it will stretch, or if we push it, it will compress. Yes or no? Tell me, yes or no? Think about it, right? If this is your driving force, right? If the driving force is in opposite direction, in outward direction, okay, then it will expand, it will stretch, right? I should not use the term expand because it's wrong. I should use the term stretch. So this is your change in length, which is increase in length, right? But if you apply a force in inward direction, right, it will decrease in length, right? It will decrease in length. So that is your compression, right, everyone? And this is your stretching. Agree? Right? Got it? So these are the two cases when you're applying a force, right? When you're applying a force, right, in this direction. Anyone have any issue in this? Tell me. Anyone have any issue in this? See, expand means, right, volume is changing, volume is increasing, but in this case, volume won't increase, na? The length is also decreasing, right? So this area will decrease and this length will increase, right? So technically, it's not the correct term, but yeah, you can use. Technically, it won't be correct. Okay, got it? You can use, doesn't matter, right? But it's fine. Now let's think about this case, right? Let's think about this second case I'm talking about. I'm just talking about the deformation. Okay, here I'm not using any term, I'm just using the deformation, right? Now think about it. Suppose it is fixed away. I hope all of you have seen this like punching bag or something like that, where you push or punch this and it try to uh, it get deformed like this. Wait, it get deformed like this, right? Right, everyone? Yes or no? Right? Then again, it come back. How many of you played with this kind of toys, right? Where you punch and then they just rebound? Anyone? Right? I hope all of you have at least seen that. Okay. Now let's take one scenario in which, right, instead of pulling or pushing, right, you're applying a force in perpendicular direction. Okay, right? In this direction. Okay, this is the direction of driving force, right? Okay, this is the direction of driving force. Now, what do you think? What is happening over here? What is happening over here? I'm not using any term because everything is same. Now, can I say that? Can I say that? Okay, there's also kind of strain or stress in that, right? There's also deformation. Yes or no? Tell me, yes or no? Can I assume this as lots of different planes, right? Lots of different planes sliding over each other, right? Lots of different planes sliding over each other, right? Tell me, can I say this? Okay, one plane over here, one plane over here, and they are sliding over each other. Got it? Yes or no? Right? Agree? Agree, everyone? Okay. Now, in this case, right, this is the actual length. If I talk about this is your actual length, right? Length. And this length is actually not changing, right? Because when you talk about this also, this is not changing. But what is changing? If you talk about, right, this is changing, right? This is changing. This is your change in position. This is a delta x or delta L, right? Instead of delta L, I'll just use delta x only, okay, or delta anything, because delta L means this distance, but this is changing, right? I'm talking about the stress, right? If you apply more force, right, it will change this position now. Tell me, it will slide more. When you talk about slide more, then the position which will change will not be the length, but this position, right, in x direction. Yes or no? Tell me, right? Yes or no? Think about it, right? Agree? There won't be change in length, right? But there will be a change in this position. Okay, so I can say that here the strain should be change in this length, which is delta x, by total length? Yes or no? Yes or no? Because when you talk about this position, any of the position, wait, this is basically this position. Delta x is not this one, delta x is whole this position, right? Because this point changes to this point. Yes or no? So this is your delta x. Now when you talk about this, so this is your delta x, right? Okay, right? When you talk about this point, so this is your delta x, right? Everyone got it? Okay. Now can you see one thing? Can you see one thing? If you talk about delta x by L, delta x by L, so you can see that this is your right angle triangle. You can see this right angle triangle, and this rod have tilted to this angle theta. This is angle theta. Yes or no? Tell me. Tilted to this angle theta, right? Yes. And what is this delta x by L? What is this delta x by L? Tell me. In mathematical term, it is delta x by L is nothing but tan theta. Yes or no? Yes or no? Because when you talk about this delta x, right? So you have to take this length. If you take this delta x, you have to take this length. If you're talking about this delta x, you have to take total L, right? It's not that for this delta x, you have to take whole length, right? Because this point you're talking, okay? So this should be your length, right? Okay, so what is constant throughout? This ratio is constant throughout. Yes or no? This ratio is constant throughout, right? So I can say that the tan theta is constant throughout. Yes or no? So this strain is basically a tan theta, which is delta x by L, right? And L is the length of the point, right? The length of the point from the base, right? Whose displacement in x-axis you're considering, right? You cannot take that this delta x in this whole L, right? Because it doesn't make sense, nah? You're talking about this point. Okay, you're talking about the strain in this point. So you should take this distance only. Make sense? Right? Right? I'm just talking about the physical parameters. I'm not naming them, right? We will just name all the type of strain, all the type of stress, right? After we discuss what are the type of deformations which can happen, right? Okay, what about third one? I hope all of you clear about this. Everyone cleared about this concept? Just raise your hand. Everyone is clear in this? If anyone have any doubt, please ask. Sumaya, Mansi, Riya, Pritam, everyone, Koshi, Krishna. Yes, yes, right? It is displaced, right? Okay. So I can say the last part, right? Basically, when you talk about the change in length, it is the point, right? Which point is changing? Which point is changing its position? Which point is deforming? So here, when you talk about this delta x, right? When this point is changing to this point. Now for this delta x, the length of this point was this distance, right? Okay, this distance. So it doesn't matter which point you are taking. The change per unit length, right? The change per unit length will be constant, right? That's what strain is, right? It is change per unit length, yes or no, right? Deformation per unit length. Okay, so here the length is this and deformation is this, right? That's why strain is delta x by L, which is basically your tan theta. Theta is your deformation angle. It is also called as the whole term, right? Stress and strain can be given different name depending on the type of deformation. Okay, we will discuss that after some time. First of all, we're just discussing the type of deformation. Okay, everyone, right? Got it? Tell me. Okay, now let's take one more example. Let's take example of sponge. I hope all of you have seen sponge, right? Or that stress releasing ball, that yellow one ball, right? Happy ball, right? What we do with them? Tell me what we do. We try to press it, yes or no? Think about it. We press it from all the direction, right? So basically we apply pressure only. Okay. Now what happens? What happens? Think about it. What happens? If you press it, what happens? Tell me everyone, what happens? it will almost reduce in size, yes or no? Wait, it is right. It will reduce in size, it will shrink. Yes, very good. Right, it will shrink. Wait. Okay, it will shrink. Now, what will happen then? Tell me, what will happen then? Okay, what will happen then? If it is shrink, yes, it's squeeze, right? Can I say that the volume is changing? Can I say that the volume will change? Yes or no? Tell me. This is, right, your initial volume, and this will be your final volume. So volume is changing, yes or no? Now think about it, right? Think about your, like that squeeze ball, that yellow one, right? Squeeze ball. Okay, I don't know what it is called as, right? And second, you take your tennis ball. Now think about it. Out of these two, which will like shrink more? Squeeze ball or tennis ball? Squeeze ball, right? Makes sense? Okay, so it's not necessary that all balls, right, or all objects will shrink or squeeze at the same, right, at the same ratio. Got it? Right? So can I say that, okay, here, change in volume per unit volume should be a parameter, right? Here length is not changing, here volume is changing, right? So here change in volume per unit volume should be your parameter for change, right? Right, everyone? Tell me, right? And stress, again, stress is obviously force per unit area. So here this force, which is basically your pressure, in this case pressure, force per unit area, yes or no? Tell me, yes or no? So if we consider all this, what are the type of deformation that we have seen? Tell me, in this, all the cases, what are the type of deformation? How many types of deformation we have seen? Tell me, think about it, guys. Tell me, how many types? Three or four? Three or four? Three. Think about it, right? First is when you stretch or pull anything or stretch. Okay, second, compress. Third, third is term called shear. Okay, right? For example, when you like think about it, right? Suppose this is a paper. Okay, so now this paper, I'm stretching this. I'm like stretching this, right? If I'm stretching like this, what is happening? Tell me. If I'm stretching like this, right? Okay, anything is happening? Tell me, yes or no? Right? Try to stretch paper. Try to stretch paper, right? Okay, so I can say this is very strong, right? If I'm stretching it, it is not like, it is not deforming, so it is very strong, right? Okay, now I'll try to compress it. If I'm try to compress it, right? Obviously, I'll try to compress it like this. Anything is happening? Tell me, anything is happening? No, right? So I can say that this paper is very strong, right? This paper is very strong when it compares, right? When I talk about stretching or compression, right? Okay, but suppose we apply force like this. Suppose we apply force like this. What happened? Think about it, right? I try to displace it. What happened? Right? It teared, right? So that is your called shearing force. Okay, that's your shear. Okay, the term that we use is shear. Okay, got it? Got it? Okay, and next is, suppose anything. I don't have any sponge ball, right? So just imagine a sponge ball. Okay, the next thing is change in volume, right? Or volume strain, right? I'll just use the term volume strain. Okay, change volume by volume. Got it? Now, when you talk about stretching, right, the term that we use is tensile, this, tensile. Okay, tensile stress, right? Tensile stress This is just the name, okay? The meaning of stress will remain same. Tensile stress, okay? Now, what about this? This is your compressive stress. Compressive stress, okay? Now, what about this? What can be, if we talk about stress in this case, what it can be said as? Tell me everyone. Yes, Ovas, we share. So it can be called as sharing stress. Okay, sharing stress, and this is, tell me, yes, volumetric stress or bulk stress, right? Or just pressure, okay? Or just pressure, okay? Right? Now, this is about stress. This is the nomenclature of stress. Now, when we talk about strain, wouldn't it be the same? Tell me, wouldn't it be the same? So this is your tensile strain, which is again delta L by L. Compressive strain, which is again delta L by L. Shearing strain, right, which is delta X by L, right? And then we have volume strain, which is delta V by V. Got it, everyone? Think about it. Got it? Because sharing stress, see, it is a name given, Karishma. It is a name given, right? Okay. Stress is same. Stress is force, restoring force per unit area. That's it, right? So just think about it. Suppose you take a spring like this, right? Suppose you take a spring like this. Okay. You try to apply force like this. So it will try to regain its position. If you talk about spring, okay, I'm not having spring. Wait, I'll just check if I'm having spring or not. I'm not having spring, I guess. Okay, so if you have spring, right? Wait, I'll just check if I have spring. Okay, I don't have a spring. I have this clip, right? I'll just suppose this is a clip, right? Suppose this is a clip. Okay. Now the clip is like this. I'm applying a force in this direction, right? I'm applying a force in this direction, right? I'm not changing the length. I'm not changing, right? I'm not pulling or pushing it. Yes or no? Think about it. Am I pulling or pushing it? This one. I'm talking about this thing. No, right? Okay. Or best is your this your scissors, right? Think about it, your scissors. Okay, now when you try to cut your paper, right, from scissor, like, are you pulling up, like pushing paper? Think about it. No, right? You are applying a force which is perpendicular and opposite direction. When you talk about scissors, what scissors does, right? So we have scissors like this, one blade and second blade. It apply a force in opposite direction. This blade will apply force in this direction. This blade will apply force in opposite direction, right? And then it will tear it apart. Yes or no? Think about it, right? Got it? So that is your shearing stress and the change in length. If it will not tear, if it will oppose the tear, okay, right? Then it is your shearing strain. Got it? And volume strain is when we change, right? Sorry, it is strain. It's not train, it's strain. Okay, volume strain is basically when the volume is changing. Got it? I hope all of you understood all these four terms, because usually students get confused, right? This is very easy, but students get confused in the terms. Okay, so that's why I just discussed everything, then I talked about terms. I hope all of you will not confused in this term, because when I was studying, I was almost like, even though this is very easy, this is very simple, I used to get confused. what is shearing, what is tensile, what is compressive, and all those things. Okay. Now let's talk about relationship. We studied one relationship, right? Let's think about it. We studied this relationship. Stress is directly proportional to strain. Agree? Agree? Anyone have any issues? Tell me. Stress is directly proportional to strain, which means if we apply more force, if we apply more stress, the change in length per unit length will be more. Or if the change in length per unit length is more, the stress is more, right? That is your Hooke's law. Okay, this is your Hooke's law. This is given by a scientist called Hooke. So it is called as Hooke's law. Okay. Now, if I talk about this, stress is directly proportional to strain. I have to use a constant, a proportionality constant. Tell me yes or no. Yes or no. Right? Now this proportionality constant for, I'm talking about general term. Okay. Generally, I use this, right? I use a proportionality constant. Suppose I used K. K is equal to strain. Right? Now, I ask you one simple problem. What is this physical significance of K? What is the significance of K? Tell me. If I'll give you a value of K, can you tell me that this object is elastic, inelastic? Tell me. If I say that K is equal to, or K is very close to 0, think about it. If K is close to 0, right? Then tell me the object is, or the material is elastic or inelastic. Think about it. Tell me. Or very small. K is very small. Will it be elastic or inelastic? Very good, Ovais. Very good, Anisha. Very good, right? So I can say that inelastic, na, it will be inelastic. Inelastic. Right? Because even though there's change in length, right? Even though there's strain, there's no stress. Yes or no? Tell me. Yes or no? If there's no stress, means there's no restraining force. Yes or no? Think about it. Like, think like this. If there's no stress, means there's no restoring force. If there's no restoring force, right? What force will make the object to come its or regain its shape, right? Got it, right? So I can say that if K value is less, right, the elastic nature will be less. Now, if K is almost equal to 1 and K should not be more than 1, makes sense, na? K should not be more than 1, right? If K is almost equal to 1, then the object will be elastic, right? Or purely elastic. Makes sense? Tell me, makes sense? Right? Got it? Anyone have any issue till this point? Tell me, anyone have any issue till this point? Anyone? Think about it. Yes or no, guys? Tell me. Clear? Okay, very good. Right? Okay, so let's see. Now I hope all of you understood the basic idea. Let's see some terms now. Okay, let's see the terms now, right? Till now I was just explaining the concept, right? Let's see the definition of some. Yes, right? Yes. So Emba, don't worry, I'll just tell you the terms, right? Okay. Now, when you talk about the terms, the first thing is elasticity. What's the meaning of elasticity? I hope all of you know what is the meaning of elasticity now, right? So basically, elasticity is the property of any substance, right? It is the property of any substance by the virtue of which it regains its original shape, right? Got it? Tell me, right? This is what we studied. Okay. Now, when you talk about the factors, right, which leads to this is first your deforming force. Now, deforming force is the driving force which we apply, yes or no? So this is your external force, right, which try to change the length or volume or shape of the body. Got it? Right? Got it? Now, what is the meaning of perfectly elastic body? When we talk about perfectly elastic body, right, it means it will completely regain its shape. Yes or no? It will completely regain its shape, right? Okay. Now, whatever we see, even the rubber and anything that we see, right? All of like there's very few substances perfectly elastic, which is quartz. Quartz is a kind of crystal, right? We won't be discussing more, but quartz is your almost perfectly elastic, right? But when you talk about rubber or steel, whatever we take, right, it's not perfectly elastic, because when an object is perfectly elastic, it means it should obey Hooke's law. Yes or no? Tell me. It should obey your Hooke's law, right? Tell me. Now, one more thing which I want to ask, right? The Hooke's law, which is stress is distributional strain, will it holds true for all the cases? Think about it. Will it holds true for all the cases? Tell me. No, yes. That should hold only under elastic limit, right? Got it? So that relationship will hold only under elastic limit. Okay? Got it? We will discuss the curve, don't worry. Okay, then what is plastic body? Obviously, which we will not regain. That is your plastic body. Okay, then we talked about internal restoring force. I hope all of you understood. Okay, now stress. What is stress? Stress is the internal restoring force or restoring force per unit area. And we know that the restoring force, right, depends on the external force. Yes or no? If we try to increase the external force, the internal force would be increasing, right? So F internal by A should be equal to F external by A. Makes sense, right? Makes sense, right? But according to the definition, it is restoring force. Okay, now this term is same as pressure, so the unit will be same of pressure. But what about the unit of strain? Tell me, what about the unit of strain? No unit, because it's changed, right? It's length by length. No, Samarth, it is not elastic. Okay, right? Now, if the stress is along, yes, if the stress, right, if the stress is along the surface of the body, right? Okay, if the stress is normal to the surface of the body, it means, think about it, right? Think about it. If I'm talking about this surface, okay, and stress is like this, then it is a longitudinal stress, or right, along the length. Yes or no? Longitudinal strength along the length. And longitudinal stress is of two types, which we have discussed, right? Tell me, what are the two types? Tell me, everyone. We talked about the stress along the length, right? But it is of two types. What are the two types? Anyone? One is already shown here. If it is stretching, right, then it is your tensile stress. Yes or no? Tell me. Yes or no? Right? So this is a tensile stress. So if there's increase in length of the body, okay, if there's a pulling force, if the volume is, sorry, if the length is changing, right, and if length is increasing, then that is your tensile stress. But if it is compressing, right, if you're pushing it, right, then it is your compressive stress. Got it? Tell me, got it? Right? Okay, but if the force, right, is along the direction, if the force is parallel to the area, think about it, the force is parallel to the area, then it is called as shearing stress or tangential stress. Got it, everyone? Got it? Okay, so we have already discussed this. Okay, now strain. So strain is change in length per unit length, or change in size of the body by original size of the body. Yes or no? Yes or no? That's the basic definition, right? That is the basic definition. Okay, because when you talk about the change, it can either be change in length, or it can either be change in position, or it can either be change in volume, right? So I can say that, okay, depending on the type of stress or type of deformation, we have longitudinal stress, which is again divided into two types, which is tensile as well as compressive. Then volume strain, which is change in volume per unit volume, right? And shear strain, which is change in length, right? And that length is basically a displacement of any point, right? Okay, got it? So displacement of any point. If you talk about this displacement, it is this distance, right? So displacement of point divided by distance between the faces, distance with the initial distance between the points. So this is your tan phi, which is phi is shearing angle. Got it? I hope all of you understood this. Imba, don't worry, the video will be uploaded, right? Okay, you can just watch it and make your notes. Okay, I'll request everyone to make a note after watching this. Now there's one more type of strain or strain, right, that we will not discussing now, but I hope all of you understood this relationship. If it is torsional, if you are twisting it, right, if you're twisting it, it is also kind of shear stress or shear strain only. Yes or no? Tell me. We are twisting something, right? Suppose if we are twisting something, it is also one kind of shear stress or shear strain only, right? But it is called as torsional strain. Okay, this is called as torsional strain when anything is twisting, right? Okay, got it? Okay, so I hope all of you understood this. Tell me, all of you understood this? Anyone have any issues till this point? Anyone have any issue, any doubt, conceptual or any visualization doubt? No, clear everyone? Okay, very good. Now let's talk about the graph. Okay, let's talk about the graph. So we know that according to Hooke's law, stress is directly proportional to strain, right? Or stress, wait, stress is equal to K into strain. So suppose stress is Y, K is a constant, and strain is X. So this equation represents what? Tell me, this equation represents what? Tell me everyone. Straight line, yes or no? Yes or no? Straight line, agree? So I can say that if any object is following Hooke's law, right, the graph between stress and strain should be your straight line, like this, right? Okay, but this Hooke's law is followed, right, only under elastic limit. Only under elastic limit, yes or no? Right? When you talk about spring, when you talk about rubber, spring, apply extreme force. What happens? It will try to, right, expand, okay, but after some point, it will be deformed permanently. Yes or no? Tell me, yes or no? Have you observed this? That if you try to expand the spring after some time, it will not regain its shape. It will be deformed. Okay, got it? Yes or no? Yes or no? Right? So I can say that there will be some point at which it will hold the, right, this relationship. Okay, and the graph will almost be straight line. Now there will be a point, the maximum point, right, the extreme point up till which it has the capacity to regain, right? Suppose we have a spring. Just think about it. We have a spring. Okay, now if you stretch it, so I can say that if you stretch it up to this distance, it will regain. This distance, it will regain. But if you move it up till this distance, right, any, even a single millimeter this beyond this distance, it will not regain, right? So this distance is called as your elastic limit. It is called as your elastic limit. Yes or no? Got it? I hope all of you understood this. So this E point is called your elastic limit, right? So it will obey Hooke's law till this point, till point P, right? It will be always straight line, but there'll be some chance, right, beyond this point, right, up to some length, which till which it can again or it can still regain this shape, and that point E is called your elastic limit. So if I have to define elastic limit, what I can say, elastic limit is a point, right, or elastic limit is a change in stress or change in soil length, right, up till which any object can still regain its shape. Yes or no? Yes or no? Right? Now, if you pull it beyond this, right, just think about spring. Best example is spring, right? If you pull the string beyond that, it will keep on stretching. It will keep on stretching, but it will not regain its shape, right? Right? Now, again pull it. So if you again pull it, this point Y, right? This point Y is a point, is basically your plastic region. It is your plastic region beyond which, okay, right? It will just deform. Okay. Now again, if you pull it more, so in some books this graph is something like this. In some books this graph will be something like this. Okay. So it doesn't matter after this point. It may be something like this. It may be something like this. Depends on the object, right? So this is your plastic limit. Beyond this, there will be negligible change in the elastic. In the strain. Okay. So in the stress, even though the strain is increasing, the length is increasing, but there won't be much change in your stress. So that's why most of the book have graph like this, okay, right? Wait, I'll just show you the other graph. Okay, yeah. So I hope all of you can see this. Tell me, right? So this is the most common graph. This is the most common graph that you will observe, right? So this is the proportional limit. This is the elastic limit. After this, there will be a point at which it will just keep on deforming. And this is called breakdown point or failure or point of fracture, right? There are many names, right? It is point of fracture means at this point, it will start to break, right? For example, if you keep on pulling the rubber, what will happen? It will break, right? Got it? Or if you keep on pulling the spring, it will break, it will try to fracture. Okay, right? That is a breakdown or failure point. Now, whole this whole region, which is a plastic region, okay. Now think about this. There might be some substance which have very small plastic region, yes or no? And there might be some substance which have very high plastic region. Now think about it, right? What about gold? Gold. Gold have very high plastic region or very low plastic region? Tell me. High or low? Very high, right? Because if I'm saying that low plastic region means it will break. Yes or no? It will break as soon as more strain is applied. Yes or no? Right? But we know that 1 gram of gold, right? 1 gram of gold can be drawn up to 2 point something kilometer of wire. Yes or no? Right? Yes or no? Means it can keep on stretching, keep on stretching, right? So I can say that if the plastic limit is more, then the object is ductile. Yes or no? Then the object will be ductile, more ductile. Anyone have any issues in this? And what about if this plastic region is very less? Suppose it is like this. Then can I say that it will be brittle, brittle, right? So if you have been given the graph, right? By just seeing the graph, can you say that an object is brittle or ductile? Tell me, can you say that? Yes, agree? Okay, okay, everyone? Okay, very good, everyone. Very good, right? Okay, so I hope all of you understood this curve. I hope all of you understood this curve. Okay, so see, when you talk about formula, formulas are very simple in this chapter. Okay, right? Formulas are very simple. You just have to calculate. Okay, the name will be different. For example, we have only one formula, right? Stress is equal to proportionality constant into strain, right? Agree? Tell me, agree? But stress are of multiple types. Stress can be longitudinal, can be shearing, right? Tensile, compressive. Strain can also be of, again, depending on the type of stress or type of strain, right? K should also change, yes or no? K should also change, right? But the meaning of K will be same now, right? Meaning of K will be same, right? When you talk about, or when you think about chemistry, right? We know that alpha, H, S, all of them have the same meaning, but name was different. Degree of distillation, hydration constant, solubility, but all of them almost have same function, right? Only the name is different. Yes or no? Right? So in the same way here, okay, the name will be different. Okay? Okay. So I hope all of you understood this. Okay. Okay. Now let's see one example. Okay, let's see one example. So here we have this. Now in this case, right, when you talk about longitudinal stress, right, longitudinal stress, right? So the force is applied here. The force is applied in the direction of 30 degree. Think about it. The force is applied in angle 30 degree. So we know that when you talk about longitudinal stress, which force we will be taking? This component or this component? Tell me. This is Fy and this is Fx. Fx. For longitudinal stress, which force will be responsible, Fy or Fx? Longitudinal always perpendicular to the surface, right? It is perpendicular to the surface, nah, right? Video is stuck. Video is stuck, right? Okay, it's fine. Yeah. So I hope all of you understood this. Tell me, guys, all of you understood this? Okay, so if we have been given a situation like this, okay, when force is making an angle alpha or beta and whatever, right? So it can be drawn into components, right? X component, Y component. So we know that this X component, which is parallel to the surface, right? Parallel to the surface, it is responsible for shearing stress, right? Or shearing strain. But when you talk about this, right, this is responsible for longitudinal stress and that too in tensile stress, right? Got it? Yes or no? Got it? Okay. Okay. Now, when you talk about longitudinal stress, the normal stress, it is represented by sigma. It is represented by sigma. Okay. And strain is represented by epsilon. Strain is represented by epsilon. And the relation is sigma is equal to, now K is called as Y into epsilon, right? K is equal to Y into epsilon. What is Y? Y is your elastic constant. Yes or no? Tell me. Y is also elastic constant because K was your elastic constant, right? But here Y is given a name called as Young modulus of elasticity. Young modulus of elasticity. Of elasticity. Got it? It is just the name given. Okay, otherwise it is same. Sigma is stress only, epsilon is your strain only, Y is your elastic constant only. Got it? Tell me, got it? Yes or no? Yes or no, guys? Okay, so when you talk about longitudinal or normal stress, you can calculate this force by this whole area, right? Got it? I hope all of you are getting this. Okay, now try to, we can solve this. Try to solve this. Everyone try to solve this example. Second one. Think about it, guys. Second one. Stress is force per unit area. That's it. As simple as that. Force per unit area. Nothing more than that. Okay. Tell me, guys. Try to solve and tell me. Think about it, everyone. So what is given? Breaking stress is given, right? Greatest length of aluminum wire that can hang vertically without breaking, density is given, right? Okay, think about it. So when we talk about breaking stress, which is basically what? Force per unit area, yes or no? Tell me, force per unit area, yes or no? Tell me, guys. Yes. And when you talk about force, this force is because of what? This force is because of what? It means if you hang something, suppose this is your aluminium wire, right? And you're hanging a mass, right? Got it? Sorry guys, yeah, got it. So I can say that in this case, which is your which force will be equal to restraining force? Tell me. If this is aluminium and the mass is attached, right, it will try to pull it. So can I say that the mass, right, or mg, which is responsible for restraining force? Tell me. The mg will be responsible for restraining force. Yes. So this f is actually your mg by area, right? Got it. And we know that mg is basically what? Tell me. Rho vg by area. Any issues? Any issues? And volume is basically area into length. So rho, wait. So it is written as F by A is equal to rho ALG by A cancelled. It is rho LG. I hope all of you can relate rho GH types. Okay. Anyone have any issue? Now this is given. This whole stress is given, right? Density is given G, no. Can you find L? Can't you find L? Tell me, was it difficult problem? Yes or no? Right? You can calculate L. Okay, very good, everyone. Right? Very good. Okay. So we already studied Hooke's law. What was Hooke's law? Hooke's law says that stress is directly proportional to strain, or stress by strain is a constant. Okay. This constant is called as coefficient of elasticity. It depends on what? Tell me. It depends on type of stress and type of strain. If I'm talking about longitudinal stress by longitudinal strain, then it is Y, which is Young modulus of elasticity. Yes or no? Tell me yes or no. Right? Got it? Now think about it. Think about it. Think about it. Suppose this example, I'm just talking about this example. In this example, right, B, C, D, they are three different type of substance which is attached together. Okay, three different type of substance, right? Okay, now Y is basically your Young modulus. Y is given as Young modulus. Now, if I talk about this relationship, let's see this relationship. Okay, let's see this relationship over here. Now, if I talk about this relationship, right? So Y is basically stress by strain, longitudinal stress by longitudinal strain, and longitudinal stress is F by A, longitudinal strain is L by A, which is delta L by A. This is delta L. Small L is change in length, right? So F into L by delta L into A is your Young's modulus, yes or no? So can I say that delta L is basically FL by A into Y? Tell me, yes or no? Yes or no? Right? So if I'm talking about net change in this, which is change in this, change in length, net change of length in this whole, right, wire, right? It is change in this plus change in this plus change in this. Yes or no? Think about it. Yes or no? Think about it. Delta LB, delta LC, delta LD. Agree or not? Agree or not? Got it? Tell me, guys. Yes, yes, Imba. That's what we have been saying from the start, na? Right? Okay. So if you see this, for this, right? For this, the length is this only, right? So delta LB is just delta LB, right? Which is just this. Okay. Got it? Okay. Now, but when you talk about this length, BC, right? So basically this point is also changing now, and this is also changing. So total changes, change in B, which is this point, plus change in this BC. Okay, got it? And what is this change in B? Change in B is this one that we have already calculated, right? And delta LBC is using this formula. We will calculate this. Got it? Got it? Tell me. So this is the changing point C? Yes or no? What is changing point D? Which is changing point C plus changing this CD? Got it? Or just calculate this separately and add them. That's what being done, right? That's what being done. Agree, everyone? Okay. Anyone have any issue in this? Tell me, anyone have any issue in this? Tell me, guys. Let me know. Let me know. Okay. Now think about it. Now, if I'm talking about sharing stress by sharing strain. Okay, sharing stress by sharing strain. Can I say that sharing stress by sharing strain is equal to Y? Tell me. Can I say this? Can I say sharing stress by sharing strain is equal to Y? No, right? Because Y is for longitudinal. It's basically the term, right? The nomenclature of the term. When you talk about sharing stress by sharing strain, the constant must be something else. Yes or no? Tell me. Yes or no? Tell me, guys. Yes or no? Tell me. Yes. Now think about it. Think about it. Can I say that if any substance, right? If any substance, okay, is not moving, then it is rigid? Tell me. Then it is rigid? Yes or no? Yes or no? Just think about it. Because if it is changing in length, then it is elastic. But if it's not moving at all, then it is rigid, right? So can we say this ratio, right? This ratio of stress and strain as modulus of rigidity, right? It is called as modulus of rigidity. Yes or no? Tell me, right? Tell me yes or no, right? So if this n, if this n is almost equal to 1, what is the meaning of this? Tell me. Or if this n is higher number, this n is higher number, right? Then it means the object is fluid. Yes or no? Right? The surface is sliding over each other, right? Then it is fluid. And if the value of this n is less, it means it is rigid. Right, everyone? Tell me, right? Think about it. Yes or no? Yes or no? Right? Okay. And here, right, shearing stress is just theta angle, which is called as shearing angle. Okay. Right? Now, think about it. Okay. What about volume? What about volume? Right? What about a volume change? Right? Now, when we talk about changing volume, it is called as bulk modulus. Okay, it is called as bulk modulus of elasticity, right? Which is basically either called as K or B. K we have already used. Now think about it. When you talk about bulk modulus, it is volume stress by volume strain. Yes or no, guys? Yes or no? But we know that when pressure is applied, volume will decrease. Yes or no? Volume will decrease. So this delta V will always be negative, because if volume is decreasing, final volume will always be less than the initial volume. So this delta V is negative. Now, in order to make this positive, I have to multiply by negative. Yes or no? Tell me. Yes or no? Right? Okay? Right? So if you talk about this, we will get this relationship. Okay, we will get this relationship. Bulk modulus is equal to, right, force per unit area into minus delta V area, delta V by V, right? And force per unit area is basically P, right? Then V by delta V, negative. Yes or no? Tell me. Yes or no? Yes or no? Tell me. Anyone have any issues? Anyone have any issues? Samarth, got it? Everyone got this? What is bulk modulus? Everyone got this? Yes, very good. Now, if you see this, right, if you see this term, right, so here F by S basically change in pressure. Now, so if you talk about this, I can also say this is minus dP by dV into V. Yes or no? Yes or no? Right? Right, everyone? And when we talk about volume strain, basically we talk about when we talk about gases, then we have a relationship between P and V, right? So depending on the condition, this might change, yes or no, this might change, right? So that is something that you have to keep in your mind. Okay, for example, when you talked about isothermal process, we know that isothermal process PV is constant, right? Okay, so P delta V plus V delta P will be 0, which means P will be minus dP by dV into V. Got it? Yes or no? If you just rearrange it, P is equal to minus V dP by dV. And this is nothing but your bulk modulus, right? B. Yes or no? Yes or no? Tell me. So for isothermal process, bulk modulus is directly equal to pressure. Okay, bulk modulus is directly equal to pressure, and this is just for gases, ideal gases, right? But when we talk about adiabatic process, right? When you talk about adiabatic process, right? So this is gamma P, which is equal to bulk modulus. So you just have to remember this, right? For isothermal, B is equal to just P, right? For this is for isothermal. That we will be using this in thermodynamics, okay, right? KTG will be using this. And for adiabatic process, B is equal to gamma P. Got it? These things that you have to remember. Okay? Anyone have any issue in this? Tell me guys, anyone have any issue in this? All of you understood till this point? Everyone understood this till this point? Tell me. Okay, so I hope all of you understood till this point. Right, everyone? So I'll just send you this. I hope all of you understood what is volume strain, shearing strain, right? Got it? We completed till this point. Yield limit, ultimate stress. These things we don't have to worry, right? These things we don't have to study, right? Young's modulus we studied. When you talk about Hooke's law, it is stress is directly proportional to strain, right? Got it? And this constant will change depending on which stress and strain you're talking about. Okay. Now, when we talk about Young's modulus, this is for longitudinal stress by longitudinal strain, bulk modulus, right? Which is basically normal stress by volumetric strain, then modulus of rigidity, which is shearing stress by shearing strain, right? Got it? We have covered this. I hope all of you understood this. Tell me, right? Okay. Okay. So I'll just share this PDF. Don't worry. I'll just post this in group. Okay. Right. We have some examples also. Please go through that. Okay. Got it? So guys, we have completed point one of this. Okay. In next class, we'll be completing this. So I request all of you, to go through the exercise. Okay. To go through this exercise, because in next class first we'll try to discuss the problem, okay, then we will solve, right? So at least if you spend 1 hour, right, you can solve all the questions till question number 8. Now there will be some good question. For example, when you talk about question of 5, right, in question of 5 you have to do integration, okay, right, you have to do integration. So if you don't get it, no issues, just try. Need students, right, you can try the examples of, or everyone, right? Everyone try examples of H.C. Verma and D.C. Pandey, right? Everyone try examples of H.C. Verma and D.C. Pandey first. Everyone, okay? Got it? Right? Makes sense that you can do? that you can do, right? Examples of HC Amma and DC Pandey. Okay, and try to complete this rotation one. Okay, I'm not giving any homework in this because this chapter is quite easy, but since we have to complete it, I have to take 1 or 2 extra classes. So try to solve this as well as the rotation one.